Good afternoon. My name is Yusuke Tamaishi from Japan, and the title is about evaluation of ground stiffness using multiple accelerometers on the ground during compaction by vibratory rollers. So first about our background, and during compaction work on construction sites, it is very imperative to verify the compaction degree, of course, and to determine the state of ground stiffness in general. The CCC, continuous compaction control, is one of the most common methods for quality control. And yeah, if the roller moves so quickly, it's too dangerous. But anyway, in any case, the CCC is one of the quality control methods that uses sensors to detect vibrations in the wheel during compaction. So the conventional method of CCC is shown on this slide. In the conventional method, accelerometers are mounted directly on the vibrating wheel. Yeah, like this. And the acceleration response from the response spectrum is measured as rolling pressure progresses. The ground stiffness is determined by disturbance in the spectrum. So using this method, accelerometers are installed directly on vibrating rollers. Therefore, it's possible for accelerometers to pick up huge vibration noise. And also, impact loading may cause sensor failure. So in this study, we proposed the following method. The accelerometers are fixed on the ground surface. Yes, and ground stiffness is determined by analyzing the acceleration response spectra obtained from these sensors. So using this method, vibration noise could be reduced, and also moreover, it prevents sensor failure caused by impact loading. There's no impact loading like this. And there's many indicators of CCC, but in this study, we use the CCV, which means compaction control value. The first Fourier transform is applied to the vibration acceleration signal to obtain the CCV. And then the fundamental vibration frequency, S0, is determined, this blue bar. And also the acceleration amplitude spectra of integral and half integral multiples of S0 are obtained like these black bars. And based on the spectra, the CCV is obtained using this equation. And in this study, the combined amplitudes in the X and Y direction were used. And also N is the number of accelerometers in this equation. So this slide provides an overview of our experiment. So embankment was built on the outdoor field of Kyushu University, and 4 accelerometers were set at the top of the embankment in this red circle to measure the acceleration spectrum during compaction. The soil material used was fine-grained sandy gravel sand, and optimum moisture content is about 10.9%, and the average maximum dry density was about 1.96 gram per cubic centimeter, and the natural moisture content during the experiment was about 8.7%. So next, I'll show you the experiment's results, and upper graph shows the results of the CCV by the conventional method. And the lower graph shows the CCV obtained by the proposed method. And these results show that the CCVs obtained by the conventional method did not show peaks at different points. On the other hand, the proposed method can show the clearly peaks at different points. And also think about the CCV rate of change. The upper graph shows also the conventional method results, and the lower graph, the results by the proposed method. And the horizontal axis is number of compactions. And CCV rate of change of the conventional method does not show any convergence trend, while the proposed method shows the convergence trend of the CCV rate of change as the number of compaction increases. So next, we also focus on the CCVs at 2 points, 4.5 meter on this lane and also 10.5 meter. And the graphs also shows like the previous slide. The upper graph shows by the conventional method. Lower one graph shows by the proposed method. The horizontal axis means the number of compactions. And these results show that the conventional method doesn't have to tend to converge the CCV. But the proposed method can converge the CCV with an increase in the number of compactions. And also, we measure the ground stiffness using different methods than CCV. We measure the coefficient of ground reaction using LFWD, means light falling weight deflectometer. LFWD is a test in which a weight is dropped freely on loading plate, and impact load is applied to the ground to determine the coefficient of subgrade reaction. So the LFWD test was conducted at the completion of 4, 8, 12, 16, and 20 rotational compactions. So these are the result of the heat maps on the lane. And also the coefficients of subgrade reaction force obtained from the LFWD at 2 points, 4.5 meter and 10.5 meter, as shown in this graph. So in both locations, the coefficients generally increased with increasing number of compactions. So in regard to this result, comparing the results with those shown on the previous slide, about the CCV. The CCV by the proposed method is closer to the LFWD behavior. So therefore, yeah, it was confirmed that the proposed method results trend was similar to the LFWD, which is very widely used methods to search the ground stiffness. So here are our conclusions. The new CCC method using multiple synchronous accelerometers based on the ground is proposed. And the proposed method outperforms the conventional method in terms of discrimination and convergence with respect to the number of compaction cycles. The convergence tendency of the proposed method is close to that of the coefficient of the ground reaction measured by LFWD. Okay, that's all. Thank you for your attention.